Yes, today we'll talk to you about what I call mechanically biased interface. That's been tricky in some material, some modelization. You need to define interface that doesn't match any physical interface. So, way to define that. And something that comes from the concept of the usage-based industry today. But we are developing a lot of very fancy mesoscale model with a lot of degree of freedom, etc. For designing their part, the industry most of the time use way simpler model with a lot of micro-scale homogenization, etc. We wanted to provide a method to be able to assess the quality of this model, and yes, and to be able to identify the good parameters. And for that, we choose test case which can seem quite simple. So composite that could be considered as biphasic at microscale. So this composite is a 3D woven composite, mainly based on carbon fiber epoxy matrix base, where we replace a part of the carbon fiber zone in one direction by gas on one of the surface. And typically, this kind of materials they want to be used for structural parts in airplane because they can combine the good global rigidity of carbon epoxy composite, but they are more resistant to impact due to the gas ions on the surface. But the problem is that for those kind of materials, our application was a part can see temperature from minus 40 degrees Celsius to 120. And due to the heterogeneity, it can appear what is called a bimetal effect. So this kind of part will bound when you repeat it. And to be able to model this effect with a simple model as possible, we need to consider two phases. So the one you see here in red and in blue. What we want to check is that is such simple model able to produce properly the behavior of the part, and how to quantify the way it's produced. So let's talk a little about the model. So we consider two phases. So the first, the one that I call carbon-carbon because it's only contain carbon zones. We suppose it has an orthotropic thermoelastic behavior. And we know quite well the property of this material because it's a standard waving used by Safran. And the other phase, that's called gas carbon, is the one containing the gas fiber. This material, behavior of this material is less known, so we estimate roughly its effective property as an initialization, and we will need to identify it to be able to characterize the model. And then for the definition of the interface, we choose something which is arbitrary but not too arbitrary, just counting the number of layer containing gas fiber and layer containing only carbon fiber. And we could see interface operation between both. But you can see it's quite difficult in this due to the waving pattern to define something which is plain and respect the suspension, but it's still quite arbitrary. And the objective is through an experimental study to be able to identify first the material property, so mainly for the gas carbon phase, and the ideal position of the interface to reproduce the behavior of the sample. And to do so, we did an in-situ experiment where we submit this sample to a thermal cycle. So, and we just apply three the initial state on three loading state. So first it was a sample at 120 degrees Celsius, and then putting it down at minus 40 degrees Celsius, and the last acquisition at coming back to room temperature just to check that the sample is stay elastic all over. on the test, also come back at this initial state. But we can check easily performing DVC and checking that on the residual there is only noise remaining when you apply a rigid body motion correction. Typically during this test, what we expect is that the sample has a behavior that you can see here. So globally, it's a thermal expansion in the 3 direction and the bonding that you can see along the Y direction. So the gas flow are on this surface facing. So here what you can see that when you hit the sample is bound toward us, and when you cool it, it's bound towards the wall. And the amplitude of this displacement is very low, and that's one part of the thing that makes this test very challenging. And here are the results of the digital volume correlation on the actual experiment. So I use the global digital volume correlation algorithm with some mechanical regularization on the particular treatment for the border of the sample. I can detail it on the main purpose. So what we can see is that the data are very noisy. In fact, the amplitude of the displacement in all the directions but Y is lower than the sensitivity of the displacement, which is 12 micron in this case. But we are still able to see, to guess that the sample behaves the good way. So we can see the bonding. And the same thing in the other direction, but as the amplitude of temperature is lower, it's more difficult to see. And these results are quite difficult to use as they are, so that's why we choose to use an identification method that is called integrated method, meaning that we directly identify the model parameter without computing the displacement field directly from the raw experimental data. So identification is just the inverse problem consisting knowing the model and some physical field to try to obtain the property of the model, so the parameter to fit in the model so that it can represent the experimental results. The classical way to do when we have some DVC or IBSim measurement is to first measure the kinematics and then perform an identification. For example, using finite element method updating or this kind of method. But here, as the kinematic measurement can induce some kind of artifact or bias, especially when data are very noisy, as in this case. So we can bypass the computation of the kinematic measurement and directly computing the parameter of the model. So that's why we call the integrated process. I will quickly also is just to show the convention how we compute the displacement field from images. Typically, we minimize the residual, which is defined as difference between a reference image and a deformed image record of the computed displacement. And what I used here was what we call global IBSim, meaning that the displacement field is expressed on a finite element basis. And the problem is typically a minimization of Gauss-Newton resolution. So this is the equation that are solved in the what we called classical global DIC. And when we want to do integrated DIC, in fact, we should not to express U in finite element basis, but in any element basis. And here, the basis is in fact built from the modelization. And the parameter we want to identify, the TP corresponds to the parameter of the model. So we will minimize this. We will minimize this equation, but we can express the Hessian matrix H on the second unknown versi of this equation with respect to the one of the classical global DIC using what we call the sensitivity field, so S, which is just the variation of the development field induced by a variation of the parameter. And typically we compute it numerically, calculating the difference between two finite element simulation. Yes. And then to set the problem, we need to know which, so how to build the vector of parameters. So we do the identification in two steps because in fact the two problems are coupled. So we identify first the material property. So all I list here are the parameters that we have in the vector P. So the thing which is interesting to say is that we don't identify the Poisson ratio because their sensitivity are very low if the displacement is very low. So we are not able to identify it properly, and anyway they will not have any influence in the displacement, a very small influence in the displacement field. And in the problem, as we only measure the temperature on the images, we don't have anything which is homogeneous to a force or a constraint. So we are not able to determine the moduli in an absolute manner. We can only determine the moduli to a factor. That's why we need to fix one of it. And the most relevant to fix is longitudinal moduli of the material we know the better. So the one which can be easily measured in another way. That's why we don't identify this young modulus, longitudinal long modulus for carbon. So I will not put the result of this identification as so much. I prefer to talk about the methodology. And these things are things that have already been done in other material and more. But the part which is more interesting is more original is identification of geometrical parameters of the model. And typically here there is different solutions to compute the sensitivity to the mesh. And what we choose is to have a mesh which will keep the same topology all along the computation, but we will move the position of the interface along the computation. The advantage of this is that we can still work with very gross mesh, so with very big elements, and we can have a continuous description of the position of the interface. The disadvantage is that we need to compute an interpolation, to do an interpolation computing the sensitivity field, and to recompute the shape function, so to recompute the Hessian matrix for the correlation, things that usually we don't do with the same mesh. So the iterations are a little longer for the identification of the position of the interface. And here, as an example, is the sensitivity of the position of the interface. Yes. So just to show how the sensitivity looks. Yes, and in terms of results, so as what we wanted is it was to check that this kind of model can be representative of behavior. The good metric to measure it is to look at the residual, so the remaining error at the end of the computation. And so what we can see at the top is the initial residue. And typically this area at the top is where we got the glass store that had a nice contrast. And the fact that we see some lunula with that are positive and negative on both sides, that means that the tau doesn't match how much we want is to reduce this as much as possible. And in fact, most of the reduction, as you can see, occur when we identify the material parameters, and then the identification of the interface weights. The amelioration is very sad, it's not so good in the image here. And in fact, but the reduction of the global residue is also small. And here you can see, so in plain lines, identified position with respect to the insect position of the interface. So the initial guess was not so bad. The thing which is interesting is that this interface is at a position that is somehow doesn't match at all what we could have found if we would have done some kind of average position on the position of the toe. And yes, quick conclusion about that is that in this particular case, the meta model is able to reproduce well the behavior of the sample. But in this case, there is a coupling between the material and the geometrical parameter. So if I have done the identification the other way, identifying the position of the interface first and the material property after, the interface would have moved much more, and the material parameter would have changed less. So there is no unicity in this case, but it could be solved if we know the property of each material before, or at least know them a little better. So that's the main reason that why we did it in identification in 2 steps. And in terms of perspective, the main objective is to use this same kind of approach in parts that are typically modeled by Safran using this kind of model with microscopic phase. And typically we can think about this kind of model. So it's a model for the blade root. So typically the fan blade, the one when you see on the part function, which are modeled because of the difference weaving pattern, etc. Yes, and add some complexity, but we don't want to have something too complex because the main objective is to have the simplest model describing what we want to see. Yes, I'm happy to answer.